Hello, everybody. Welcome to the 15th lecture of the Statistical Foundation on Reinforcement Learning. This is we're going towards the end of the quarter, and this is the second last lecture on offline reinforcement learning. So after I finish teaching about offline reinforcement learning, we'll move to the new phase of the course on project presentations and feedback and so on. So this is really the second last lecture that I will cover technical materials in details. So before I start the lecture, so I wanted to say that homework 3 is released. So according to the original schedule of the course, homework 3 was a little bit delayed, but I also, because of it, extended the deadline. In addition, so homework 3 has 5 questions. So now you can choose between question 4 and question 5 and do only one of them. So hopefully that will make it easier for you guys to manage towards the end of the quarter. So the due date for homework 3 is June the 2nd. So unlike previous homeworks where you have long extensions and you can submit anytime you want throughout the quarter, the last one, like this is somewhat hard deadline, because after that I think I have a week of time to submit your grades. So if you need another couple of days after June the 2nd, that's fine. But yeah, make sure that you submit the homework like within a week of June the 2nd. Okay. So I haven't sent out. I finished like checking out all the midterm milestones that you guys sent, and excellent work in putting together the midterm milestone. And it looks like most of the groups are making excellent progress towards understanding the paper, and some of you guys even proposed some interesting extension of the results in the paper with improved parameters when they are theoretical analysis. And in other cases, like you guys proposed to actually reproduce the experiments in the paper by running their code and perhaps modify the code a little bit. And I think those are truly awesome. So please make sure that when in your project presentation, you include some of those materials and share the excellent finding with the class. And one thing that I emphasize in my midterm milestone feedback to all of you guys is that it is a good idea in your project presentation that you go by a somewhat structured fashion. You define the problem, you try to formulate the problem in the Markov decision processes that we learned. If it's different, for instance, if the problem in the paper that you're reading is a partially observed setting, you should say that. You should say what's the difference between the setting that's considered in that paper and the setting that we learned in this class, and whether it is an infinite horizon setting, whether it is finite horizon setting, are the state transitions stationary or non-stationary? So what are the state space and action spaces and so on? When function approximation are being used, you should also comment on whether they're using a model-free approach, which approximates, say, the Q functions, or the model-based approach, which they approximate the transition dynamics themselves. So this helps everybody else in the class to appreciate the paper that you've spent a lot of time reading by connecting things, by connecting your project to what everybody know as a shared knowledge of the class. All right, so I will within this week I will send the schedules for the project presentations. I will try to make it such that I'll try to make it such that based on the I guess I could also discuss with each one of you on the schedule if you disagree with my plans, because it's a schedule that's spanned over 2 weeks, so some of you will have more time to prepare for that. But yeah, don't worry too much about making the presentation very polished. So it will be somewhat informal, and each group member will have like some time to share your results, either using presentation slides or using a whiteboard kind of setting if you have access to a writing pad, right? So I'll send more details within this week, and starting next week we'll move on to a project presentation. All right, so this lecture is going to be continuing our topic on offline reinforcement learning. So we've covered OPE already. We've covered how we can extend OPE to offline policy learning or policy optimizations through the uniform convergence argument. In the last lecture, today we're going to finish the topic on uniform convergence and show how we can make use of the uniform convergence argument to obtain an information theoretically optimal offline policy learning algorithm. Okay, so as a recap, in the last lecture we talked about how the in the tabular Markov decision process setting, the several of the different algorithm design ideas that ends up getting polynomial sample complexity in terms of ball parameters. In particular, they break the curse of horizon without depending on exponentially on the horizon h. So these methods are the tabular marginalized importance sampling, the naive model-based plugin estimator, and also the fitted Q-learning estimator. So this fitted Q-learning is a fitted Q-learning for policy evaluation for a fixed policy pi, rather than the standard fitted Q-learning for policy optimization. But we've seen that all these three estimators, they are actually identical to each other in the tabular Markov decision processes setting. And we also showed that through the variance analysis, which I sketch out the details, how you can get the variance analysis for the tabular MIS, that you actually obtain a very strong notion of optimality. So first of all, they are minimax optimal information theoretically on the in terms of the rate. When we by rate I mean we are ignoring a universal constant and maybe a logarithmic factor in the convergence bound. So we see that TMIS and fitted Q-learning, they achieve improved polynomial dependence on H and on S comparing to the naive approach of using, say, simulation lemma and the approach that doesn't require the actions to have finite cardinality in the MIS. So it turns out that this H square over N times DM, where recall that DM is a smallest probability of all state and action, and T in your under your exploration or logging policy such that exist policy pi and d pi SA is strictly positive. So whenever this happens, and then we choose the smallest probability. So this is an exploration condition, which says that your logging policy actually explore every pair of SNA that are relevant for policy optimization, right? So under this condition, we can actually show that this is square root of H square over NDM, where N is the number of trajectories you collect if information is theoretically optimal. That means that no other algorithm can achieve better rates for the entire family of offline learning problem under the same condition, under the same DM, H and N parameter. So notice that S and A isn't really in the expression, so it is actually hidden in DM. So arguably the best possible situation for this family of problem is when is when dm is equal to 1 over SA. So this is when your logging policy actually uniformly explore all state action pairs. Then it becomes very similar to the generative model problem. And you can see that when you choose dm to be 1 over SA, then you recover the h square SA over n bound that we have seen from the generative model. Yeah, another thing is that n is a number of episodes. So if you replace the number of episodes, and each episode is h steps, if you replace this n with number of steps, so n is equal to number of steps t over h. So you get the more standard h cube SA over n optimal error that we have obtained in the generative model setting. So everything matches up nicely. And offline setting can be thought of as a strengthened version of the generative model setting that makes a more realistic assumption on the how the data is being collected, rather than they are coming from an IID sampling oracle or a generative model. Now the offline data is actually coming from running certain policy mu. Okay, and the OPE convergence for TIMIS and Statistical iterations, they are actually they are actually even more they're actually even stronger than information theoretic optimality in the minimaxes. They are actually optimal for every example separately, which means that for every pair of target policy pi and behavior policy mu or logging policy mu, and for every MDP separately, then the MSE, the mean square error of what you can achieve through this model-based approach is actually per instance optimal up to a low order term. And low order term also doesn't have exponential dependence on any parameters. So in some sense, for large n, like this matches the primary or lower bound up to low order terms. So really, like, no other algorithm can do better than these model-based approaches. Besides like very small improvement in the low order terms. Okay, and then we, after having that nice realization of the OPE for a fixed target policy pi, we move on to talk about offline learning problems. And the one idea that we discussed last week was to generalize the empirical risk minimization idea from the machine learning like standard supervised learning setting, and in which we are minimizing the error on the training data, but we expect the trained classifier to generalize to new data set, right? So how do we replicate that in the reinforcement learning setting? So the idea is that we can just use the empirically observed training data to come up with the offline policy evaluation estimator for every pi separately. And so this becomes a function of pi, and you can think about it as a negative of the empirical risk. And then this natural algorithm that finds the policy that maximizes this empirical negative empirical risk is the one that hopefully will also generalize. In some sense, it will be close to say it will be close to the ideal situation where we're trying to try to find the optimal policy that actually maximizes the V of pi. So this is a true risk, a true negative risk, and true reward, and so hopefully the performance of pi hat is going to be quite similar to the performance of pi star. Okay, and to formalize the idea, the typical approach that's used by empirical risk minimization is through the so-called uniform convergence argument. So if you can show that with high probability, simultaneously over all policy in the policy class, then the OPE estimator V hat pi is close to its population level counterpart, is close to its expectation. If the OPE estimator is unbiased, then this uniform convergence. So uniform is associated with this the supremum or maximum over all policies. then we can instantiate this pi to be pi hat and also to be pi star. And then by simply subtracting, we had pi star, adding, we had pi star, subtracting, we had pi hat, adding, we had pi hat. Then we can group these two together, bounded by epsilon, and group these two together and bounded by another epsilon. And due to the pi hat is the argmax of the empirical estimated reward, then this is smaller than 0. Therefore, you can bound this by 2 times epsilon. Okay, and this argument is very powerful. So it says that if we can somehow construct a uniform convergence argument, such as long as this policy class pi covers these two policy of interest, then we can obtain this policy learning bound with the same error. Yeah, it's the same suboptimality bound. Okay, and we made this assumption called DM assumption, which is an exploration assumption. I explained it just now. This is to simplify the discussion on the optimality, because and in some sense this is yeah, you cannot really get around like similar assumptions on exploration, because the goal is to use offline data to identify the optimal policy. And if you do not have such exploration assumption, then the optimal policy might not really be like in some sense measurable, right? Suppose you never really visit this state action pairs at all, and then there happens to be a large reward associated with this state action, and it happens that this state action is what the optimal policy is visiting all the time, then there's really no way that you can figure that out like using the information that are given to you through the offline collected data, right? So this kind of assumptions are necessary, like if we are trying to find the near optimal policy. On the other hand, you could weaken such assumptions and come up with, but then the learning goals will also have to be weakened. So hopefully, like, I'll have time to talk about some of those alternatives in the problem setup in the offline reinforcement learning setting in the next lecture. We are considering 3 different policy classes pi in the last lecture and in today's lecture, and they are the family of all policies, including policies that are randomized, that take different actions with a certain probability. And if we restrict ourselves to deterministic policy, then it's without loss of generality, because we know that there exist an optimal policies that are deterministic due to the Bellman optimality equation. And there's a third policy, data-dependent policy class called epsilon empirical optimal policy, which is essential and for us to get optimal offline learning algorithm. So we'll talk about each one of these in the next couple of slides. Like I wanted to just mention that the distinction between all policy and deterministic policies, they are not very different, in the sense that even though the space of all policies are much larger and it is a continuous set, it doesn't really make the policy class substantially larger. So in the sense that if you are coming up with a covering number of the space of all policies, and then it will be very similar to the covering number of the space of all deterministic policy, right? Which is simply a to the power of h times s, right? So yeah, from that regard, like we will focus on deterministic policy and this data-dependent empirical linear optimal policy in this class. And the lectures were based on the paper Ying and Yu Bai and myself wrote last year. All right, so this lecture will finish our analysis on deterministic policy class and deriving the uniform OPE results for this class, and then we will also try finishing the local uniform OPE, which uses like in some sense a dual argument to the one that we make for the deterministic deterministic policy class. So we'll see a lot of the proof ideas and the technical details are actually shared among some of these analysis. Also, so many of those techniques we've already covered them in the previous lecture. So I'm gonna go over them when, and point those out whenever we run into this situation where, oh, this is something that we've learned before, and now we are just applying something that we learned from lecture 3. And then we'll see a couple of times that this happens in today's lecture. All right, so in the last time we made some progress on the deterministic policies. So just as a reminder, we're dealing with a tabular MDP setting with a finite state and finite action and finite horizon. And this in this setting we assume the time inhomogeneous or time varying or non-stationary style of episodic MDP when the transition kernels P1 to PH, they could all be different. And the reward S and A also differ at different T, right? So this makes the number of parameters to describe the model H times larger than the stationary counterpart or the infinite horizon counterpart. But we'll see like how it helps us in obtaining the tight dependence on everything in the proofs. And well, so the deterministic policies are pretty straightforward. The idea is very simple, and we've used that many times in this class now. So it involves counting the number of deterministic policies, right? So last time you guys gave me the correct answer, which says that the cardinality of the deterministic policy class is a to the power of sh, and the reason is that at every state, at every time point, right? So there are sh of them. You need to decide which action to pick, right? So that's a to the power of s and h. So if we are given a high probability OPE bound in a form of say for sup of all pi in deterministic v hat pi minus v pi smaller than say 1 over n times dm h square log yeah, if we have a pointwise, like for a fixed pi, if we have log 1 over delta, maybe some big O here, then we can use union bound by choosing delta to be delta tilde over a to the power of sh, right? And then we can get the uniform convergence bound in the form of this is with probability 1 minus delta. Then with probability 1 minus delta prime, we can get this to be smaller than. First of all, let's copy everything over. And secondly, we'll substitute this delta with 1 over delta prime, and then you'll have a to the power of sh, right? And this sh, since they are on the exponent, they goes outside. You will have additional factor of s. You will have additional factor of h. So at the end of the day, this argument will give you a square root of h cubed s over n times dm. Okay, so that's the idea under the condition that if we have a high probability OPE bound. So in the previous lectures, when we talked about OPE, we always focus on the mean square error analysis, which isn't a high probability OPE bound. In particular, we cannot convert it directly into such a form of bound with a log 1 over delta dependence on the failure probability, right? So that's the issue that we need to resolve. But yeah, the theorem is exactly as I wrote. So with some minor differences, so there's a high order term that goes to 0 much faster, and there are some additional factors in the logarithmic vector. But otherwise, so that's the argument that we're going to take to prove this theorem 3.1 or 3.5. Okay. Yeah, I wanted to emphasize that this offline learning, like this bound is optimal in terms of its dependency in H. So no algorithm can do better than H cube, and it is potentially suboptimal in S. But is it really? So we'll see. We'll see. Yeah, we actually will not be talking about that, but we have some new results that seems to hint at information theoretically this factor of S cannot be removed in general. Now, the question really boils down to how do we obtain a high probability point-wise OPE bound, right? So we started a little bit on this in the last lecture. We sketched out the steps of the analysis. So involve 4 steps. So the using some of the tricks that we've learned in the pointwise OPE lecture. So the first of these is the fictitious estimator technique, and which says that let's condition on some nice events, right? So in this offline setting, the offline data is collected by running some logging policy, and those logging policy may get, like, we may get lucky, we may not get so lucky. So we can define such event ET associated with step T, and T is a time horizon, time step in the episodic MDP. There are total of H steps, and this NSA means the total number of times that in your logging policy at time T you visited state ST and AT pair with this many times. Right, so this is the expected number of times that you visit, and what this condition is saying that like in your offline data you see what you expect to see, right? What you see that the number of times you visit every state in action is roughly like at least half away, a factor of half away from your actual probability of seeing seeing those state action pairs, right? And we can prove with multiplicative turnoff bound, which we work out in details in the past lectures, that these events hold simultaneously for all T, ST, and AT with high probability. And so what are these fictitious estimators? So we are using this. So all these are refreshers of things that we've already learned. We are using tilde to denote these fictitious estimators. It ranges from V tilde, IQ tilde, the value function tilde, the transition probability, transition kernel tilde, and R tilde, and so on. So all these tilde means exactly the same thing. They means that if these events are not true, and on this PT and RT, we're going to be substituting the true value, right? We're going to substitute the true PT and the true RT if these events are not true, and those like subsequent changes are propagated to our estimate of the fictitious fictitious marginal state action visitation, on the pi. It got propagated to D to the mu indexed by T. It got propagated to the Q function, V function, and eventually to the OPE estimator, right? And after that, this simplifies the problem so that we can analyze something that's more well behaved, and it doesn't suffer from that pathological case of a very small number of visits to a particular pair of state and action that happens with a small probability. And through multiplicative turnoff bound, we show that with high probability, the actual estimator and the fictitious estimator, they're actually identical to each other. Yeah, and we don't care what's going to happen in those failure probability because it happens with a very small chance. And the next thing is to decompose the error. So this error decomposition and it helps us to get rid of the unknown reward, right? So the reward function, so in this more general setting, we assume it is unknown. We are getting one sample at each state action pair. But we've seen that through error decomposition last time, then the reward part of the variance, the reward part of the issue can be easily dealt with using Hofstein's inequality and union bound, right? So by error decomposition, we can handle the reward part of the issue and the transition kernel part of the issue separately. And then the next thing is to handle the part of the error due to the error in the estimated transition kernel. And then this requires us to decompose the estimated occupancy measure minus the so d tilde ts minus dt of s. You can decompose this into a summation of different quantities, and each individual quantities have something to do with error that you observe in the transition kernel. And we saw that it was a martingale, and actually we'll talk about that again, and to convince you that this is a martingale. And once we certify this as martingale, and the next argument that we use is a concentration style of argument. So in this lecture, we've learned Hofstein's inequality and Bernstein's inequality. They apply to IID random variables, right? We also learned the McDiarmid inequality as a generalization of the Hofstein's inequality. They apply to IID random variables, and we can take some Lipschitz function of a sequence of IID random variable. So martingale concentration are a further generalization of that towards a different direction by getting rid of the IID assumption. So all you have to do, all you need is that the sequence of random variables, they are the sequence of random variables, they are martingale. And more generally, so you only need like exchangeable conditions rather than independence condition. And this slight generality is actually useful for us to analyze these online algorithms that requires us to use the data, the random data that collect in the past to make decisions for the future, right? So Friedman's inequality is a Bernstein version of the martingale concentration. So it's a generalization to the Bernstein's inequality to martingales, similar to a Zuma Hofstein's inequality is a generalization of the standard Hofstein's inequality to martingales. Yeah, so we'll see what Friedman's inequalities look like and how to apply that in today's lecture. So a recap of step one. So yeah, I've actually already covered this. The fictitious estimator. So makes it easier to analyze because everything becomes unbiased now, and the bias is a main issue. Like even in the multi-arm bandit setting, when we were analyzing the variance of its OPE estimator based on the model-based approach, right? It is really the whether the number of action that's take being 0 or not that's creating this bias, right? So under the fictitious estimator assumption, then like we don't have that issue. So everything is biased, and all the Bellman equations and so on can be applied naively. And yeah, by the multiplicative turn-off bound, we also show that these are actually the same with high probability. So which means that it suffices to analyze the fictitious estimator. And the second step is to handle the noise in the reward, which we did this error decomposition. And this term is due to the error in the estimated marginal state action visitation. And we'll see that they translate into the error in the estimated transition kernel. And this part is easy to deal with by a simple Holder's inequality, since this one is a probability distribution. And then it becomes bounding the it becomes bounding the L infinity norm of R tilde and RT, which we can apply Hofstad's inequality and union bound to handle very naively. And it doesn't actually give us like the crazy dependence on the different parameters, and this is exactly what we expect. Actually, this is smaller than the quantity that we expect. So without loss of generality, this is the double star part is something that's easier. Okay, so the third step is slightly less straightforward. So it involves decomposing the error from the IMIS estimator of the state action visitation. So d tilde pi t, you can think about it as a probability distribution defined on S and A. So it is the same as the marginal state distribution multiplied with the pi t of A of S. So this becomes a joint distribution of state and action, right? And this R is a state action, the true expected reward at state S and then taking action A, right? So what we can do is to decompose this expression into a summation of individual terms, and each one of the terms depends on, say, this is your empirical estimate of the initial state distribution, and this is the error of your empirical estimate of the transition kernel. So this T is yes, sometimes we use T to denote the matrix, and other times we use P. Yeah, it's confusing, and sometimes we see inconsistent notations. But yeah, at least in today's lecture, so when we see this T matrix, it denotes the like this denotes the matrix where so this is a matrix in R S by SA. So it denotes the state transition. It denotes enumerating all the possibilities of the input and output of this state transition at step H. So it is transitioning from H minus one, AH minus one to the H step, and T tilde is a fictitious estimator of this quantity for all SA and S prime by enumerating all of them. Like so T tilde H is the fictitious version of the plugin estimator, right? So you can see that this decomposition decomposes the error of the marginal visitation into a summation of the individual errors that are due to the state transition estimates. And naturally, like these value functions pop up. So these are actually capital V. Yeah, these are the true value functions from the original MDP. So even though this expression appear to be slightly different to things that we've learned before, I argue that you can actually just prove this by what you have already worked out in homework 1, question 5 on the simulation lemma. So this is a particular application of the simulation lemma. So with the knowledge that this d tilde thing is times RT is really just a model-based approach, then you can simply apply the simulation lemma and decompose the error into this expression. So you work that the details out in the question 5 of homework 3. Okay, now so let's check that this is actually a martingale. So recall the definition of the martingale. So there is a sequence of random variables and you condition on each one of them. So there's a sequence of random variables that I'll keep adding to the transcript, which I call this data, this dt minus 1. So in our case, D0 is nothing, and D1 is actually all the data that's that's from D0 together with So dt dt is d1 to t minus 1 together with the parallel exploration of running the login policy, which gives you the s t I a t I r t I. So these are for I from 1 to n, right? So these are the sequence of random variables that we consider, and this martingale is a martingale over the time steps of the Markov decision processes, rather than an online learning algorithm like taking actions and that. So that's basically a different T, right? So we're taking the columns of the data matrix and then go over the individual columns in the martingale. Okay, so now in the definition of the martingale, we require that this random variable, random sequence satisfying xt given the information that's available up to this point is equal to the previous one. So essentially it requires a martingale difference to have expectation 0. Okay, so and the second condition is that the expected value of the absolute value of xt is always bounded, which is easier to check. So let's check that this is the case. So below I'm basically just copying over from the previous expression of this martingale decomposition. So let's check that this conditional expectation of xt is actually the same as xt t minus 1, right? So how do we how do we deal with it? So let's take the conditional expectation given the t minus 1, right? So first of all, so dt minus 1 contains all the data that we have from d0 to from d1 to dt minus 1. Therefore, this one is fixed, right? This is completely determined by the data that we have already collected. Now, this term we can decompose this into the last term. So this is the t pi t tilde h minus t d tilde pi t minus 1, right? And then summation from h from 2 to t minus 1, we h t tilde h minus t h d tilde pi h minus 1, right? So this is fixed, since it only depends on the data from the past that's already captured in the data. So this is fixed. This is obviously also fixed, and this is also fixed, right? So for all h up to t minus 1, because we have already collected data. So the whole thing on the right hand side, these part, they are fixed. And what are they? They are actually xt minus 1. So xt minus 1 is determined by the data, and it's not a random variable once we condition on the filtration dt minus 1. And this is the only part that introduces a new random variable. And the only part that introduces the new random variable is from here. This is the only part that is random. So when we take the conditional expectation here, let's discuss two cases. In the case when in the case when this is 0, right? In the case when we are unlucky and we're running into this unlucky event, then the fictitious estimator actually fixes that, right? So this becomes exactly 0, and which checks the condition. And in the cases when this is not when we are actually lucky and we observe sufficient number of data points for each one of these state Gaussian pairs here, then we know that this expectation, this t tilde is unbiased. Therefore, it also gives us a 0, right? So all this together check the first condition of this is a martingale. And the second condition, xt absolute value. So how do we see that this is finite? So notice that our martingale, we only care about it up to step h. Therefore, by just trivially using the fact that the value function is bounded by h, and this is a probability distribution, and it gives us the sum of h, and this is h. It gives us h h square. It gives us h square upper bound. Therefore, therefore, we also check the second condition. So this is martingale, right? So now it remains for us to show that in this martingale, it converges to its expected value using martingale concentration. And the particular martingale concentration that we'll be using is called Friedman's inequality. So like I said, this is a generalization of a Zuma-Hofstein's inequality into the Bernstein style, right? So we can see that if xi is a martingale, and we need to check two conditions. The first condition is that with probability 1, this martingale difference, so the neighboring two values of the martingale is bounded by m, and secondly, the sum of the expected the sum of the conditional variance for all possible sequence of realized random variables here, right? So notice that this quantity is random because this f I minus 1, it is random. Therefore, this is not the same as the sum of the variances, but rather this is the random quantity that needs to be bounded by w, right? It needs to be bounded by w. So basically, we need some kind of a upper bound for w and some kind of upper bound for m in order to apply the Friedman's inequality. Okay, and if we look at the result, it says that with high probability, the martingale converges to its expected value with this perturbation, right? And this error is proportional to the square root of this sigma square, and it is proportional to this capital M. So this should remind you of the Bernstein's inequality, where it's like Bernstein's inequality is like we're dividing this x by n, ex by n, right? So yeah, in the Bernstein inequality, you get something that's very similar, which says that in the leading term you have this 1 over n square root of the variance of this individual summand minus xi minus 1 log 1 over delta. And there's a low order term, like if m is bounded by a quantity that's similar to the variance, which, so this is square root of n, and in the second term you get 1 over n and m and log 1 over delta, right? So this is Bernstein's inequality, and you can see that by multiplying both sides by n, which is the length of this martingale, then you recover something similar to Bernstein's inequality, because this w and sigma is an upper bound of this w with probability 1, and it is a summation of n quantities, and it's inside the square root. Right, so this term should be the leading term with a square root, and this term should be the constant term, square root of n. This term should be the constant term without that, without any dependence on it. Okay, so that verifies that this is something that's at least semi-familiar to you. So you know Bernstein's inequality, and this is a generalization of that to martingale. And in order to apply this to our problem, we need to do two things. We need to bound this m. We also need to bound the variance of this quantity, and then calculate the sum of this conditional variances, which turns out to be quite tricky. So in our case, we needed to apply like a generalization of the Friedman's inequality, which relaxes the condition a little bit. So these results are due to Chong and Liu, 2006, which says that it suffices to show that with high probability, then such martingale differences is bounded by m, and similarly with high probability, and then such a sum of the conditional variances is bounded by w, or bounded by sigma square, right? So that additional flexibility helps us to apply a Friedman's style inequality to our problem of interest. Okay, so now let's move on to see how we can actually deal with that. So we'll start by bounding M, and then we'll try to bound the W, and this is sigma squared. So you'll see some of these techniques are things that we are already pretty familiar with, and we've learned that and practiced that many times. Okay, so to begin, we'll try to bound M with high probability. So the argument is that we will take a union bound, right? We'll take a union bound over all state and action. We'll take a union bound over all T. So it suffices to first bound this for a fixed T, and then union over all T. So what we can do is to take the difference between the two martingale. We've already seen that. Since the expected value of this xt is xt minus 1 plus this quantity, so the last summand within the first system of summation is the martingale difference, right? So we just copy this over, and then this is what we got, and then we can apply so notice that this is a matrix in the middle of the size S by SA, and this is a vector. Right, this is a vector by size SA, and this is a vector by size S. Right, so you can group this matrix with either the left hand side or the right hand side. So now let's decide to group this matrix with the left hand side, and then apply Holder's inequality with the L infinity L1 type. Okay, and what do we know about this? This is a probability distribution. So this is a state action visitation probability. So this is equal to 1. Now it remains to bound this quantity, and what we can do is to just now we actually discussed this. So I argue this is the same as the indicator of ET minus 1. First of all, why is that? Because if the event if this event is not true, then the fictitious loss estimator will simply output TT, and then the difference will be exactly 0. And now I can extract out the maximum by the definition of L infinity norm. So this will be the maximum, and inside the inner product is a summation over ST. So summation over ST, so it will be T hat TST given S and A minus TST given S and A, and this got multiplied with the VT hat ST. Right, so this is just applying the definition of this L infinity norm, and I guess what we can do is to then apply the definition here, right? So notice that this is a plug-in estimator, so we can rewrite this as first of all sum over ST 1 over n. 1 over n SA, so this is the number of times S and A is visited at time T minus 1, and summation over I from 1 to n, the indicator of S T minus 1 I is equal to S, ST minus A T minus 1 I is equal to A, and ST I is equal to ST. Okay, and this got multiplied with VT ST, right? So here's a trick that this indicator, together with this summation and with this VT, it's essentially evaluating this function VT pi at the particular realized value of STI, right? So what we can do is to rewrite this. So we'll see this trick several times today. So we'll exchange the order of summation by pushing this summation of ST inside, so that these two can be grouped together as an evaluation of VT pi. So what we get is 1 over n SA and summation over all I, such that ST minus 1 I is equal to S, and AT minus 1 I is equal to A, right? So this get rid of the first true part of the indicator, and the second part of the indicator on ST got combined together with VT pi. Yeah, so this is an evaluation from the inner product, and for those who are familiar with RKHS, this should remind you of the properties of reproducing kernel Hilbert space, but in this case, it's straightforward. So basically, in this summation, only one of them is non-zero, and everything else is 0, and you get V pi T ST I, right? And minus the expected value, minus yeah, so I forgot to minus expected value, minus the T S T A T S sorry ST S A and V pi T S T, right? So this is the expected value which got plug in here, and then the same expected value of VT given S and A, right, is given in the last line. So what is this? So this is really the convergence of IID random variables. So notice that we're conditioning on the past data, which really gives us exactly this, which makes this random variable fixed. So condition on the past data up to time t minus 1, and condition on and given that this event is true, so now we're inside, and this becomes a simple like mean converges to its the average converges to its expected value kind of thing. So we can apply Hofstein's inequality to this. And union bound over all state action pairs and over all T. And then what this says is that we'll end up getting this expression. Super for all T and super for all possible state and actions. Then we have M being bounded by this quantity with high probability. Okay. Now let's move on to bounding bounding the W parameter, right? So this is to bound the sum of the conditional variance, and the first step of that is to write the like individual summand of this conditional variance. So we recall that we want to assign some high probability bound of W, which sums over H from 2 to H, the variance of this xt plus 1 given the VT, right? So this is what we need. So let's bound for every let's bound this for every T separately first. So so what we can do here is to just plug in the definition of xt plus 1. So this will be the like recall that it is an inner product, like from the previous page. So this is an inner this is an inner product kind of thing. So we will replace this. First of all, like given so the variance of xt minus 1 is the same as the conditional variance of xt, because xt plus xt minus 1 is fixed when we condition on dt, right? So this simply becomes the variance of the variance of the martingale difference, right? So we can write this by expanding the definition of inner product. So this will be sum of xt at. So this is the inner product that's That's outside, and sum over st plus 1, and v pi t plus 1 st plus 1 t tilde t plus 1 minus t plus 1 st plus 1 of st and at. What remains is this input marginal state distribution, state action distribution at step t under pi. So this is a fictitious estimator that we have estimated, but this is like given dt, this is fixed. Okay, and this is the thing that is random, right? So how do we calculate this conditional variance? So the same trick. So first of all, like under the case when this is when we're not lucky, then we don't have any variances, right? So we can essentially extract things out by replacing this with a definition of the fictitious estimator that comes with indicators, and noticing that this dt pi is fixed, we can extract it out, right, from the variance operator. So let's do that. So with these two things, so first of all, indicator et and sum over st and at, and I argue that I can also extract this st and at out of the variance. And why is that? And then the reason is that this chi tilde t plus 1, so they are like the conditional expectation estimator, and when we condition on different st and at, we are actually using the disjoint subset of the data. So let's say that the data is partitioned into so this is st and at, sti ati, st and ati equal to st and at, and equal to st and at, st tilde and at tilde. And the part of data that we use to estimate these two conditional distributions, they're actually disjoint with each other. And since every trajectory is independently drawn, then we can actually partition this st and at and extract it outside the variance. Because for independent random variables, the variance of x plus y is equal to variance of x plus variance of y, right? If x and y are independent. So now condition on dt, like these are really just independent. So we can extract this out, and inside we'll have variance of s summation only over st plus 1 and vt plus 1 pi st plus 1. And let me just copy this over. Given dt, and well, this term, like I said, is fixed, so it can be further extracted out. Square. Okay, so I applied three things. The first of the independence of the data for estimating the transition kernel given a different st and at pair, and secondly, I applied this this quantity being fixed, so I can extract this out. So if variance of constant times x, right? So I can is equal to c squared times the variance of x. So this simply follows from the definition of the variance. And if you are having any trouble with that, just work it out from first principle. And now we simplify the expression a little bit. And the next thing that we could do is exactly the same as what we did in the last in the last slide, right? So now we have a difference between the quantity of that's empirical estimated and the mean, and then it is taking an inner product with this quantity, right? So this is still the same thing. Now if we decompose this t tilde into the individual summand, the individual observed version of st plus 1 I, then that we can substitute that st plus 1I into this evaluation of this value function, right? So let me write it down. So we'll have the indicator of ET, summation of st and ET, and then the variance of 1 over n, st, and at. This is the total number of times these two are observed at step t, and summation over I from 1 to n such that sti is equal to st, ati is equal to at. Yeah, so let's restrict our attention only to those parts, to those particular partitions of the data. And then this summation over st plus 1 is just collapse into this vet plus 1 pi st plus 1 I. Right, so this makes this the univariate quantity that we can deal with, and whether or not we subtract its mean, like, doesn't matter, because we are calculating the variance, right? So what I'm saying is the variance of x is equal to the variance of x minus expected value of x, right? So the remaining part that deals with this this t plus 1. So this is a true value. So that's the expectation. So we can throw it away without changing the variance at all. Right. So we've simplified the expression a little bit now, and we are left with dt to the pi of st and at square. Okay, and that yeah, sorry, I missed st and at, conditioning on st and at inside this variance. Wait, yeah, not inside here, but rather okay, yeah. The last thing to realize is that this variance, given the entire data set dt, now really really becomes like a conditioning individually on this individual on this individual sample, right? So notice that notice that these are IID samples. So VT plus 1 pi ST plus 1 I. So these are IID samples. These are saying that, let's say that we pick this partition, and each individual elements of this quantity, they are independent to each other due to the n trajectories being independently drawn, and then we can apply this formula for the variance. So when xi is independently drawn, this is equal to 1 over n variance of x1. Okay, and what is that? And what is this variance of x1 here? It is the conditional variance of the value function given that you are at st and at. Okay, so ultimately we can write 1 over et summation of st and at and d to the pi t st and at square. So let's take this out, and by this independent the variance of independent the average of the independent random variables, we will recover this 1 over st and at in the denominator, and what remains is the variance of the conditional variance of vet plus 1 pi st plus 1 I st plus 1. Yeah, I can just take the first one, right, since they're all equivalent, given that st of 1 is equal to s and at of 1 is equal to at. Yeah, which recovers exactly what we wanted to prove. Okay, so that's how we bound one of the terms in this in this summation, and it remains to just sum them up, right? So it remains to sum them up. So what we can do is to sum this variance up, and what we'll get is not really whatever that's on the right hand side, but rather so let me write down what we'll get. We'll get, by applying the lemma just now, we'll get the sum over this quantity. So you will have n s and summation. So first of all, summation over all ST and AT pair, and indicator and E T over the number of times you observe this ST and AT in your N episode at step T. And on the numerator, you got this d tilde pi T S T AT square. Right, so you got that, and it remains is the conditional variance of the value function. Yeah, so that's what you got, and this variance is about the variance of this ST plus 1 into the like due to the state transition. So what this is saying is that so if we can like somehow bound this d tilde in a form of this thing being smaller than, say, maybe a constant times d pi of t, st and at, right? So notice that like this is something that we should expect, right? So we got this we got this before. We showed that the expected value of this d tilde pi is smaller than like some constant, very small we got something similar to this in the OPE lecture when we analyzed TMIS. So in this case, like if we can show that, so for instance, this happens with high probability, then we can substitute the numerator like to be something that depends on dt of pi rather than dt pi of tilde, right? So basically what we need to deal with is this coefficient. So first of all, on the ET, so remember what ET is. ET is an event such that n, st, and at and t for all st, at, and t is larger than half of the d mu t, st, and at, right? So this is the event for all st, at, and t, right? So when this happens, what can we do? We can simply replace this coefficient with half d mu t, st, and at. And if in the numerator, like we can replace this d tilde pi square with some constant square times d pi t, st, and at square. If we can do this, then this becomes something that's already familiar with us, familiar to us, right? So st and at. Outside, there's summation over t from 1 to h and variance of this conditional variance. At, right? So this is something that's familiar to us from previously. So in this lemma 0.4, in this lemma 0.4 from the last lecture, we've shown that even though these are the summations of h elements that can be as large as h square, we can actually bound this by the rho max. So this is maximum importance weights which get rid of one factor of this d pi and d mu, so we can replace it with rho max. And for the remaining thing, it's actually the expectation of running the policy pi and doing on policy evaluation. RT. Right, and we know that the variance of this, and of course there's this leading factor of dividing by n. Yeah, the leading factor of dividing by n. So what we can get is that this variance is bounded by h squares, right? So ultimately, we could come up with a bound that looks like we could. Yeah, so let me organize this a little bit. So ultimately, we can rewrite this bound into some constant times the maximum importance ratio between the pi and mu over n and multiply by h squared, and this is this is further upper bounded by this quantity. So using the fact that this importance weight is the ratio of two probability distribution, if you take the numerator to be 1, and then you get 1 over dm, right? So this is a slightly weaker bound than what we can obtain here. So all these are conditioned on that we can bound this quantity on d to the pi, and how we can do that is it's what we're gonna talk about in the next slide, right? So this is something that typically we could get away with doing something that's cruder than a very fine-grained analysis. So it turns out that we needed to do like the martingale decomposition for d theta again, right? So we can apply the martingale decomposition of d theta again, and then apply the and then show that similar to previously, we can show that with high probability that this vector martingale, this like vector of martingales have this L infinity norm, like of every segment of this to be smaller than this quantity with high probability, right? And then we can apply Chong and Liu style of Zuma-Hofstein's inequality. So notice that we don't need to apply the Friedman inequality now, but rather we only need to apply the Zuma-Hofstein's inequality and union bound over individual coordinates. Then we can already get a like sufficiently good bound for our purposes, which looks like the following, right? So it says that it goes to 0 at the rate of 1 over n with some dependence on h, right? So I'm not going to go into details on how you do this because we've already covered something that's like significantly fancier, but on the high level, so these are the approaches. We talk about how to get the martingale decomposition, and once you have the martingale decomposition, you basically do the martingale concentration bound for every coordinate of this vector of martingales separately, and then take union bound across them all, and then you can get this this bound and take union bound over t, then you end up getting this quantity. So all the union bound and all the doing every coordinate separately will only introduce additional logarithmic factors, right? So that's the beauty of having a concentration bound with exponential tail. And you can hide a lot of complicated stuff in that exponentially small quantities where focusing on the leading factors. So now let's apply this to the bound of W and then put everything together, right? So first of all, now that we have we have a bound that says that d theta pi t minus d pi t L infinity norm is smaller than h over n dm and some log factors. Okay, so but this is not what we want. So what we can do. So what we can do is what we want is to bound this quantity in terms of dt pi, right? So what we can do is to add and remove dt pi minus dt pi plus dt pi square, and then use the like pseudo triangular inequality for the square quantity, which gives us 2 times the dt square plus 2 times the d tilde pi minus dt pi square. And this is where we can apply like this upper bound that holds with high probability. Right, so essentially, like by doing this, we now have an additive upper bound in terms of what we want and some additional factor. And this square is helping us because now this term becomes the order of h over n dm log say log 1 over delta kind of thing. So it goes to 0 at a much faster rate of 1 over n. And if we substitute into our expression for w, so what is it? It is here, right? So we can substitute this into this expression, right? And then we get exactly what we want in addition to some additional additive factors in the end. So what we can get is this w is smaller than and this is a summation of the conditional variance of xt given dt minus 1, sum over t from 1 to h, right? So by this, we show that with high probability, this quantity is upper bounded by rho max over n h square plus plus the product of NDM multiply with rho max of NH square. Right? So these terms, I call them like low order terms. Right? So essentially, at the end of the day, we can bound the summation of the variance to be this quantity, and then we can bound the like we've already shown that with high probability that like the maximum deviation in every time step in this martingale is bounded by this quantity. So putting them together, we can plug them into the Friedmann's inequality by substituting this sigma by substituting this sigma square and this m. So what we end up getting is order 1 over n, and what we're getting here is order 1 over n, and plus some residual terms that are little o, order 1 over n, say n 1.5. Yeah. So I claim that by like using this rho max, we can actually get something that's slightly tighter than what the paper has stated in terms of everything using dm. Yeah, but this is easily bounded by 1 over n dm as well, right? So you'll have dm here and 1 dm here, and everything else is even higher order term. Okay, so that concludes the proof for the yeah. So that concludes proof for the high probability pointwise OPE analysis, and then by simply applying a union bound to this, so notice that this is h square, and by simply applying a union bound here, you have additional factor of h and additional factor of s, so you will get the uniform convergence bound with that epsilon being HSA over delta square root, right? So this uniform over all policy, all deterministic. Okay, so we'll take a 5 minutes break and we'll resume at 2:32, and then we will finish the rest of the lecture by just very quickly sketching the analysis for the local uniform convergence on the new family of problems. See you guys at 2:30, 2:32. All right. Welcome back to the class. So we'll so just now we talk about the uniform convergence theorem for the family of all deterministic policies and obtain the convergence bound of the form H cube S over NDM log HSA over N plus like a little plus a low order term. We see that doesn't actually give us the desired bound for offline learning, because we expect the in the offline learning, like we should get an epsilon to be on the order of H cube over NDM, right? Without the dependence on S. At least without explicit dependence on S. And in the paper that we've also shown that this is the information theoretical optimal rate for offline learning. So any algorithm, optimal algorithm should be able to achieve this rate. However, if we use the union bound argument over the deterministic policy, so that doesn't give us what we want naively. Right, so we also consider this uniform convergence over all policies, which is something that I'm gonna have to skip. So there are some interesting technical points in the proof, but the results wise, so this is dominated by not really dominated. So in some cases, like you can improve the dependence on S when you want the probability of success to be really small. But in general, this is a slightly weaker result in terms of the dependence on H comparing to the uniform convergence for all deterministic policies. So what I wanted to focus on is something that's slightly different, which deals with the so-called local policy class. And by local policy class, we mean all policies pi such that on the empirical MDP that you observe, so this empirical MDP are estimates based on your plugin estimate of the state action transition kernel and then the reward function. So on that family of MDPs, which I denote as V hat, the corresponding value function is V hat, and if the for all policy pi such that the L infinity norm of this difference of this policy pi measured in terms of the empirical MDP, value of the value function on this M hat is close to the empirically optimal policy. So this is the optimal policy on the empirical MDP, right? So in some sense, if we are not constrained by computation, we can just run policy iteration on this to get what a policy iteration or value iteration on this to get what pi hat is, right? So for any policies that are given, this is a quantity that we can actually measure, right? And near this pi hat star policy, there is a family of policy such that it satisfies that the difference in terms of the empirical value function is smaller than some quantity epsilon opt, right? When this happens, and if this epsilon opt is smaller than some constant, and this constant, like it is like really just a constant, it doesn't depend on the number of episodes. So this is a somewhat larger local neighborhood near the empirically optimum policy. So for this family of problems, we can show that as long as the number of policies larger than this, then you can obtain the optimal like uniform of policy evaluation. Notice that this is stronger because you can plug arbitrary D1 hat into this by taking the inner product of these to get the V pi to get this to get an estimate of V pi, right? So this is sufficient for us to obtain a uniform OPE. And if we restrict ourselves to this local policy class, we can obtain a stronger epsilon parameter, which doesn't depend on S, and this is the optimal rate. So comparing to what was available before, so we saw that the same rate was achieved in the generative model setting. So these are the problems of probabilistically solving MDP on the IID generative oracle that we've learned in the I think lecture 2 and lecture 3, and comparing to that, like ours achieved the same result with some improved parameters on offline collected data, right? So with offline data actually collected from some a login policy, and then we explicitly depend on the exploration parameter of that offline policy. So this is the optimal, and I think by far, like I think the first and one of the like current state of the art that achieves the optimal rates in offline reinforcement learning. So how it works, how to prove that theorem is actually somewhat interesting. So just now, like we started off by a martingale decomposition of this d hat minus d, right? So just now we started the martingale decomposition from the occupancy measure point of view. So this is coming from the dual LP of the Markov decision processes. On the other hand, you can start from the primal LP of the Markov decision processes by directly working with the Q value functions. Like if you do that, and then you write down the Bellman equations, you take the difference of the Bellman equations, and you can prove this simulation lemma, right? So by applying simulation lemma on this finite horizon episodic case, you can decompose the policy the Q hat function on the empirical MDP and the Q hat function on the true MDP. You can decompose the difference in a very similar way to something that's very similar to martingale decomposition that we had before. The key difference is that previously, like this part is approximate and this part is exact, but now like this part is exact and this part is approximate. So in homework 3 Q5, you will see that like it's really a matter of applying simulation lemma to bound the Q hat pi minus Q pi, or to bound the Q pi minus Q hat pi. Because from this point of view, you can think about the true MDP to be an approximate MDP of the to be an approximation of the approximate MDP. By just toggling the two M and M hat, then you can obtain the two different views of the same difference, and you will end up getting like slightly different quantities, and in one of the quantities you are estimating the occupancy measure, and in the other quantity you're estimating the value functions. But what's common in these two ways of decomposing the differences in your estimator is that they all depend in every step on the model-based estimator of the state transition kernel. Okay, so when you apply simulation lemma here, and you can do error decomposition with this simulation lemma by decomposing them to the individual error of individual error of p hat minus the individual error that's coming from different transition kernels. If you go by a naive like simulation lemma based approach, and then the next thing to do would be to apply the L infinity norm bound on this quantity, right? So you will apply the L1 norm bound on the estimated probability, right? As we did earlier in lecture 3, which uses a McDiarmid inequality argument. Like, so some of you might still remember that. And then you bound the L infinity norm of this VH of pi, and that gives you the uniform convergence, because because this part, once you take the L infinity norm bound, it doesn't matter which pi that you are which pi you are choosing, right? But that's a somewhat crude argument. So now let's decompose this error in a slightly different way, right? So let's decompose this by adding and removing the empirical optimal policy, right? So let's do this by adding or removing the approximate value of the empirically optimal policy pi hat star, right? By doing that, we can decompose this error into two separate terms: the triple star and 4 stars. Like do you call that quadruple stars? And with the quadruple stars, like we start by bounding the quadruple stars, and first of all, we can see that this is something that's a product of two quantities, right? And the first quantity goes to 0 as n gets larger, and second quantity, by our assumption, is smaller than epsilon opt. And if we choose epsilon opt to be small, then this will give us something that's small, right? So since this is how local, this local policy class is what we control, so we can potentially first bound it and then choose this epsilon opt parameter later. So the idea is to first use the fact that this gamma, so this gamma is a transition matrix, so it's a probability transition matrix of by applying the Markovian kernel multiple times under this policy pi hat. So you've seen from homework 1 that like no matter how many times you apply a transition kernel and that matrix, you will end up getting like a multi-step transition kernel with the same dimension, right? And since this is a stochastic matrix, it has a like operator norm in terms of L1. So if the input is a probability, the output is also a probability. If the input has bounded L infinity norm, then the output will also satisfy the same quantity. So by using that, we can get rid of we can get rid of this quantity, because we know that this is smaller than 1. Okay, we know that this quantity is smaller than 1, so let's drop that, and it remains is the product of the two error terms. And for this, we can also afford to do something that's pretty crude. So by using our assumption that this pi hat, whatever pi hat that we choose, is nearly empirically optimal, and then using, say, this is a pi hat is in the local local policy class, then we know that the L infinity norm of this quantity is smaller than epsilon opt, right? So then we can extract it out, and what remains to be done is to show that the to show that this is small. Like in fact, we can what we can do is to fix every pair of S and A, and then apply Holder's inequality. In this case, this becomes pH of dot SA minus pH dot SA inner product with 1, right? We can bound this with L1 norm of P hat H SA minus pH dot SA L1 norm multiplied with 1. Right, L infinity norm, that's why. And this is something that we've worked out. Again, from lecture 3, we've shown that this is smaller than square root of S over the number of times that you observe S and A pair and some logarithmic factors. And we got that through the McDR meeting inequality, and also by bounding the by bounding its expected value, right? So by doing this, this improves the like slightly the parameter from S to square root of S in the original paper. That concludes the quadruple stars. And for the triple star, what we can do is to to use the following key observation. So this is really the key thing that gets into work. So whenever we consider on whenever we condition on the empirical optimal policy, then this product. So even though this term and that term, they are both random variables that depend on the data set, they actually depend on different part of the data set. So if we condition on D to the h minus 1, then we can see that this p hat of h is an estimate of only this current step, right? So this makes use of the properties that the Markov decision process is time varying, because we can only use the state transitions at time h to estimate this probability. So if we do that, then we have p hat of h, and this value function, like it is something that's interesting because it is a function that depends on all possible like you can substitute in all possible s, right? So the value of this function, like taking the current s h as an input, depends only on the future data after h. Right, so one of these quantities only depends on the data in the past, and the other random variable only depends on the quantity in the future. So condition on the data that's observed up to h minus 1, they are actually independent random variables, which allows us to use the trick that we've been using like for twice already in today's lecture, and we're going to be using it for the third time, which says that this quantity you can write it as 1 over NSA sum over I, such that SI H is equal to S, SH A, HI is equal to A. You sum over all only the relevant data, and then you can actually substitute this SH plus 1 I inside this V. So it becomes, instead of a vector, a scalar random variable that we can apply Bernstein's inequality for. Right, so by applying the Bernstein's inequality on this quantity, on this univariate convergence of the random variables to its mean, we can knock out a factor of s, right? So by doing this, applying Bernstein's inequality, then we get this. Yeah, it has all the right dependence, and this n is a lower bound of NSA, right? And by our fictitious estimator, and also by our assumption assumption on dm, we know that this n is you can take this n to be dm multiplied with over 2. Okay, so we're getting to the end of the lecture. Just bear with me. If we put everything together, and then we can continue with this bonding of these two terms. And if we put everything together, we get this like slightly more complicated looking expression. But if we look at it more closely, the leading factor really only depends on things of interest. Depending on the variance, and then there's another term that depends on the epsilon opt. So the bonding of the summation of the variance is like somewhat technical, but it is very similar to how we control this variance previously using the law of total variance, and also using the fact using this cute lemma 3.4 by saying that the summation of the variances, conditional variances can be bounded by the variance of the on-policy evaluation. The sum of the variance of the sum of the R. So what you need is a conditional version of this lemma. So by extending this lemma, and also by replacing this V hat with H by adding or removing certain quantities, such that you can somehow bound it with the variance of the true value, and then you can apply this conditional version of lemma 3.4 to get the quantity that are of interest. And after we do that, it remains, so notice that this is only bounding this Q hat T rather than Q hat 1, right? So it remains to propagate these changes by recursively applying the same quantity backwards. So notice that the right-hand side also depends on V, and it further depends on, you can bound this by Q minus Q, right? You can bound this by this quantity. Since we're enumerating all possible input to these functions and bound them in our infinity norm, so we can construct this recursion. And once we have this recursion, we can roll backwards and then eventually get the difference between the Q1 estimator, right? And finally, so what it suffices for us to just calculate everything and put down the complicated expression and set this t to be 1, and then choose this epsilon op to be sufficiently small. And the idea is that, like, once we choose this to be this quantity, then the terms that depend on the epsilon op will no longer be the dominating factor, and it will be merged into the leading term, which has a right dependence on everything. Okay, so in summary, we've like finished the offline reinforcement learning part of the lecture. The key techniques that we use is is uniform convergence. We talk about several different kinds of uniform convergence, including the global uniform convergence, which will obtain square root of s h cubed over n dm for global. And for the local uniform convergence, what we obtain is a h cube n dm, and this is optimal. And this certifies that the empirical risk minimization is indeed minimax optimal, and this is the best that any algorithm could do. And in the lectures, we've covered all the essential tricks on the theoretical analysis. What I didn't talk about is offline reinforcement learning other settings, and so it's, for instance, infinite horizon setting and finite horizon setting. So with a stationary transition, so these problems are slightly more challenging. And Ying and myself, we had a couple new papers that addressed those questions, and finally settled these open problems of offline RL in all settings of interest. We've also shown that this, for the global uniform convergence, this h cube s, at least this s factor, is actually required. And you cannot do global uniform convergence without depending on this s. So there are some interesting observations in this new paper as well. And in the next lecture, I will talk a little bit about offline reinforcement learning with function approximation. So in particular, the linear function approximation. And for those who are interested in this line of work and interested to know some of the remaining open problems, feel free to talk to me. And of course, like read our papers on these topics. Yeah, I thank you for your patience, and I will see you on Wednesday.